Hi everyone, in this video we'll be discussing infinite series. In particular, in this video, we'll determine when infinite series have finite sums. We'll understand the convergence of a special type of series called a geometric series, and we'll analyze another special series called the harmonic series. So to begin with, let's start with sort of a motivating question. So imagine I wanted to add up the sum 1/2 plus 1/4 plus 1/8 plus 1/16. So you might be able to see the pattern here, right? Each time my denominator is doubling. So a half plus a fourth plus an eighth plus a 16th plus a 32nd, so on and so on and so on. Okay. Now, what I have done here actually is I've represented the shapes sort of various areas. And if you'll notice, each one is 1/2 of the size of the previous figure. So I can sort of think of this as being a rectangle with height 1 and base 1/2. Okay, and then this has the same size base, 1/2, but it's half as tall. Okay, so it has total area 1/4. This first one has total area 1/2, right? And now, again, this has a base now that's half of the previous base. So this is 1/4 with the same height, which is 1/8, or sorry, which is same height, which is 1/2. Got a bit ahead of myself. But now when I go to find the total area of this, it's 1/4 times 1/2, which is 1/8. So you see that these areas correspond to a half, a fourth, an eighth, a 16th, a 32nd, and a 64th, right? And then dot, 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 so on and so on, right? So one sort of very clever way I could get at understanding what this is, I could think about sort of trying to rearrange all of these different rectangles into a different shape that I could easily find the area of. So one trick I can play here, right, is if I sort of take these shapes and I rearrange how I stack them, right, you can sort of see that as I start stacking these, I could arrange this infinite sequence of rectangles into this square. And you notice, I mean, I have this sort of dot, dot, dot up here, but you can sort of imagine I could continue stacking all these things in this way so that sort of in the limit, in some sense, as I added them all in, I would end up with this square. Well, if you remember back to before, this had height 1/2. Each of the, or sorry, this had height 1. Each of these had base 1/2. So the total base here is 1/2 plus 1/2, or 1. And so the total area of this figure should be 1. So it seems like if I take a half and a fourth and an eighth and a 16th and a 32nd and a 64th and a 1/28th and 2/56 and so on and so on and so on, it seems like if I rearrange them, I get this figure, which has area 1. So it sort of looks like this ought to sum to 1. Okay. But I mean, this is a little iffy, right? I mean, I've done sort of a lot of hand waving here. I'm sort of hoping, again, that this sort of infinite pattern continues based on what I see from maybe trying the first, what's that, sort of 6 terms. It's not totally clear that that's actually going to work out. But it seems reasonable, like maybe these things ought to add up to 1. Now, already you might be feeling sort of uncomfortable. You're going to feel a lot of weird things are going on as we talk about these sort of infinite sums. And that's because a lot of your intuition about sums comes from working with finite sums, sums with a finite number of terms. But now I'm really thinking about adding up an infinite number of things. Now, there's an immediate part of your intuition that wants to say, you know, if you add up an infinite number of things, then that's got to be infinite, right? But the answer to that is actually no. And if you think back to our discussion earlier of improper integrals, maybe that's not so surprising, right? We saw that we could integrate a function from, say, 1 to infinity that was always positive and still get a finite area under that curve, right? So similarly here, when we add up an infinite number of terms, it is possible to still get some finite value. But admittedly, the first time you see this, it can feel a little bit uncomfortable. Let's see if we could try to maybe make this a little bit more precise, though. Okay, so I actually written out a few more terms here, and let's think about how we might analyze this. Now, again, I said a lot of our intuition about things comes from finite sums. I like dealing with finite sums because I can understand them. So let's think about some finite sums. So I could take this sum, and I could take just the sum of the first term. So just the first term. Then I could take the sum of the first two terms. I'll call that S2. Okay, so that would be 1/2 plus 1/4. 1/2 plus a fourth is 3/4. Okay. Then I could take the sum of the first three terms. Okay, well, that would be 1/2 plus a fourth plus an eighth. We already know 1/2 plus a fourth is 3/4 plus an eighth gives me 7/8. I could take the sum of the first four terms, right? The sum of the first four terms would be 1/2 plus a fourth plus an eighth plus a 16th. Okay, and if you do that calculation, you'll get 15/16. Okay. I could even take one more since I've got 5 terms written out here. I could take the sum of the first 5 terms. And I notice that that gives me 31/32. Okay. Now from this, you might start to see sort of a pattern. And the pattern appears to be that the sum of the first n terms is, if you look at our denominators, they are 2 to the first power, 2 to the second power, or 4, 2 to the third power, or 8, 2 to the fourth power, or 6. So it seems like in the nth term, I'm getting 2 to the n. And notice that the numerator is always 1 less than that. So it looks like the sum of the first n terms, written another way, would be 2 to the n divided by 2 to the n, or 1, minus 1 divided by 2 to the n. Okay. Now, this gives me the sum of the first n terms. Now I could ask myself, what happens as n gets really, really big? Well, as n gets really, really big and goes off to infinity, this term is going to go to 0, right? As n goes to infinity, 2 to the n gets really, really large. So 1 over 2 to the n is going to go to 0. So I have 1 minus 0. So notice here that the limit as n goes to infinity of s sub n is equal to 1. So we found the sum of the first n terms, and then we let n go off to infinity, and saw that as n goes off to infinity, I get 1 here. Now notice, what I've done here actually is I have defined a sequence based on this infinite sum. And now what I have determined is that this sequence converges to 1, and therefore I think that this sum ought to converge to 1. Now, it turns out this is precisely how we want to think about infinite sums. Okay, so let's actually formalize this so that we can apply it to any number of infinite sums, not just the one we're looking at here. So imagine I have some infinite series. Okay, so we're going to call these sums infinite series. And the way to sort of conceptually think about this notation, so this sigma notation is gives me a sum. It's for I values going from 1 to infinity. So in this case, this would be like a sub 1 plus a sub 2 plus a sub I plus all the way on and on and on out forever to infinity. Okay, so this is just what we call an infinite series. Then if we have an infinite series, we can define what we call the nth partial sum of the infinite series, which we'll define S sub n, and it's just the sum of the first n terms, right? So instead of n going from 1 all the way up to infinity, the nth partial sum is just the sum of the first n terms, right, of the sequence. Okay. So again, going back to sort of my example before, so that sequence I could have written, or that series I could have written as the sum, whether we call it I or n or j or k, doesn't matter. We can call it anything we want. Maybe I might call it n equals 1 to infinity of 1 over 2 to the n, right? So notice that that's the same as when n is 1, this is 1/2. When n is 2, this is 1 over 2 squared, 1/4, 1/8, so on and so on. And what we actually did, right, or we calculated the partial sums. So the first partial sum would be the sum from n equals 1 up to 1, so just the first one, which is just 1 over 2 to the 2 to the 1, or 1/2. S sub 2, right, was the sum n equals 1 to 2 of 1 over 2 to the n, or just 1/2 plus 1/4, which was 3/4, and so on and so on, right? So we calculated, actually the things we calculated are exactly these things we want to call the nth partial sums. And in fact, in that case, we were able to determine that the nth partial sum, S sub n, could actually be written as 1 minus 1 over 2 to the n. So we actually found an expression here for any nth partial sum. All right. So why does that help us? Well, if we have an infinite series and we have this sequence of partial sums, then if that sequence of partial sums converges to a limit, then we say that series, the infinite series, converges to that limit as well. Okay. So really, what this is a definition that tells us what we mean by the infinite series. We mean that the infinite series converges if, as we take and expand this partial sum to include more and more terms, that sequence approaches some finite value. Okay, so in this case, right, we determine that the limit as n goes to infinity of S sub n was equal to 1. And therefore, we could actually just say that the sum n equals 1 to infinity of 1 over 2 to the n, we could say it converges, or we could just write that it is equal to 1, okay, because it converges to the value of 1. Okay. Now, this sequence, right, I've written it as 1 over 2 to the n, but notice that you could also write it as 1/2 to the n, okay, right? By rules of exponents, this would be 1 to the n, which is just 1 over 2 to the n. So it's equivalent notation. But writing it this way, it's easy to see that each term, right, is 1/2 of the term before. You're basically taking the previous term and multiplying it by 1/2. So we saw when we talked about sequences, right, when you have a sequence where the next value is determined by multiplying the previous value by some fixed number, that's called a geometric sequence. This is what we call a geometric series. So it's a geometric series because consecutive terms in the series have a common ratio. So 1/4 divided by 1/2 is 1/2. 1/8 divided by 1/4 is 1/2. 1/32 divided by 1/16 is 1/2, right? So each subsequent term is 1/2 of the previous term. So this is what's called a geometric series. We want to see if we can explore those actually in a little more depth. Okay, so this is going to build off our work here with this sequence 1/2 to the n, or 1 over 2 to the n. All right, so in general, when we talk about a geometric series, we're usually thinking about a series of this form. So we have some fixed multiple a out front, some constant a, and a constant r, which tells us sort of what each consecutive term is multiplied by. So the series is a times the sum n equals 0 to infinity of a times r to the n. Now, if I were to write out terms of that, right, when n is equal to 0, because I'm starting at 0 here, then I get a times r to the 0, but r to the 0 would just be 1. So that's my 0th term is just a times r to the 0, or a times 1. Plus, then I'll get an a times r to the first power, plus an a times r to the second power, so on and so on, right? Eventually, I'll get an a times r to the nth power, and then we'll keep going and going and going. Okay. Now, what I'd like to know is there any way for me to sort of understand, what's happening to the value of this, infinite series? Okay, so again, in order to understand an infinite series, I first need to understand the sequence of partial sums. Okay, So let's give ourselves a little room here. Okay. So in this case, I can write out my nth partial sum. So this would be the sum of the first up to the nth term. So this would be a times r to the 0. R to the 0 is just 1, so that would be a plus a times r plus ar squared plus, say, ar to the n minus 1 plus ar to the n. Okay. And now, let's see, if I were to multiply both sides of this by r, what would I get? I would get ar plus ar squared plus ar cubed plus, this would be an r to the n minus 1 times r would be r to the n plus ar to the n plus 1. Now what I want to do actually is I want to subtract both of these. So I want to take and I want to write an expression for s sub n minus r times s sub n. So if I were to subtract these, right, you'll notice that a lot of things will cancel, right? So I will get an AR minus an AR. And I'll get an AR squared minus an AR squared, and an AR cubed minus an AR cubed, and A. So all this stuff will cancel. And then I'll get an AR to the n minus an AR to the n. And so at the end of the day, all I'm left with that doesn't cancel is in this first piece, I'm left with an A. And then in the second piece, I'm subtracting off an AR to the n plus 1. Okay. And so the reason I've done this now is you can see I can actually factor an s sub n out here. I'll get s sub n times 1 minus r. And I can factor an a here. This would be a times 1 minus r to the n plus 1. Okay. And so I get that the nth partial sum is equal to a times 1 minus r to the n plus 1 over 1 minus r. Okay. Now, again, to analyze this infinite series, we then need to think about what's going to happen to this as n goes to infinity. Well, if you look here, the only place there's any dependence on n is right here. So really what we need to understand is what's going to happen to r to the n plus 1 as n goes to infinity. Well, that's going to depend on the value of r. If r is a value that in absolute values is less than 1, then a number that in absolute value is less than 1 raised to higher and higher powers is going to go to 0. So think about 1/2, right? 1/2, as you raise it to higher and higher powers, gets smaller and smaller and smaller. And that's true of any number whose absolute value is less than 1. Okay. If the absolute value, if r was equal to 1, you'd actually have a problem here because this would be 0. Okay, and so you wouldn't be able to say anything. And if r was bigger than 1, then this thing would actually run off to infinity and this whole thing would diverge. Okay, so what we get here is that the limit as n goes to infinity, so let's deal with the case where r is less than 1 in absolute values. So if r is less than 1 in absolute value, then as n goes to infinity, that's going to go to 0. And so you'll be left on the top with just a, and on the bottom with 1 minus r. So this is if the absolute value of r is less than 1. If you are dealing with any other value of r, this limit will be infinite. If the absolute value of r is greater than, I just realized that cut off on the bottom. So, but if the absolute value of r is greater than or equal to 1, that limit will be infinite. So what we can say is that this converges to a over 1 minus r if the absolute value of r is less than 1. And it diverges if the absolute value of r is greater than or equal to 1. So now what we have here is we now know how this works for an entire class of functions, or sorry, of series, in this case, the geometric series. Okay. So let's actually then take a look at some examples and see how we can use this in practice. All right. So let's say you're given this series and you want to determine, first of all, whether it converges or diverges. And if it does converge, you might like to know what value it converges to. So the first thing to do is to recognize that A, this is in fact a geometric series. I have some constant times another constant to the nth power. And its limits are the limits that I am used to from that previous, going from 0 to infinity. So now when I look at this, I can sort of just say, oh, okay, I can identify this as my A value. And I can identify this as my R value. And because this is in the form sum n equals 0 to infinity of A times R to the n, and since this R value in absolute values is less than 1, this will converge to A divided by 1 minus R, since our R is 1/2, and absolute value of 1/2 is 1/2, which is less than 1. Right? So in this case, all I need to do is plug in my A value, which is 2/3, over 1 minus my R value is 1/2. And so this converges, and it converges to 2/3 divided by 1 minus 1/2 is 1/2. That's the same as 2/3 times 2/1, or 4/3. So for this geometric series, we can pretty quickly determine that it not only converges, but we now know what it converges to. It converges to 4/3. Let's look at another example that's not quite so straightforward, but with a little work, we can determine whether it converges or diverges. Now let's look at this example. Now, on the surface, you may go, oh, this is almost exactly the same problem. But we have to be a little careful because well, there's sort of two things different about this problem. So if we sort of flip back and forth between the two, sort of do the find the difference thing. The first difference you might notice about this problem is that it starts at 1 instead of at 0. And the second thing you might notice is that instead of being 1/2 to the n, this is 1/2 to the n plus 1 power. Now, the results that we know are for series of the form n equals 0 to infinity of A times R to the n. So what we would like to do is first do a little manipulation to this series, and then see if we can use this to help us figure this out. So the first thing I'm going to deal with actually is the exponent piece. Okay, so if I look at this, I can think of this as the sum n equals 1 to infinity of 2/3 times. Now, I don't like that that's n plus 1. I really want that to just be n. So I can write 1/2 to the n plus 1 as 1/2 to the 1 times 1/2 to the n. And so the first thing I get is that this is the sum n equals 1 to infinity. Now, if I multiply these together, I get 2/6, or 1/3, times 1/2 to the n. All right, so now that's looking a little closer, but I still have this issue, right? This is A times R to the n, but I still have this issue that it's going from 1 to infinity instead of 0 to infinity. So this is where I would say, well, okay, if this were from 0 to infinity, I could calculate that, right? So I could come over here and say, I know the sum n equals 0 to infinity of 1/3 times 1/2 to the n, right? This is less than 1. Okay, so it does converge. It converges to A over 1 minus R. So this is going to converge to 1/3 over 1 minus 1/2. That's 1/3 divided by 1/2, which will be 2/3. Okay, so I know this sum, but that's not the one I was asked about. So now I sort of ask myself, well, what's the difference between this and this? And the answer is one term, right? The 0th term, right? If I look at this value, so if I sort of take this piece of information, I have that the sum n equals 0 to infinity of 1/3, 1/2 to the n is equal to 2/3. But I could rewrite this. This is the sum of the 0th term plus the first term plus the second term plus the third term. I could rewrite this as the 0th term. So the 0th term would just be 1/3 times 1/2 to the 0. It would just be 1/3 plus now the terms starting at 1. So really what I've done here is I've broken off this 0th term. So right here, this is like my 0th term. And then just kept the first through the rest of them all in the sum. Okay. Well, now this is nice because this is the quantity that I want. Okay. And so I can just subtract 1/3 from each side. So I'll find that this sum in the green box is equal to 2/3 minus 1/3, or 1/3. And so the value of this series does in fact converge, and it converges to the value 1/3. Now, a quick note of caution, okay? It's tempting to skip over the bit where we worry about whether or not R is less than 1, okay? But what I want to show you is that that's actually very important, because if we're not careful about that, it can lead us astray. So just imagine momentarily that instead of, well, in fact, let's not even look at this one. Let's look at a slightly different thing. So let's say that I gave you the series sum n equals 0 to infinity of 4 times 2 to the n. If you weren't careful, you may just look and go, well, that's A and that's R. And so this is equal to A over 1 minus R. And so that's 4 over 1 minus 2, which is 4 over -1, which is -4. And so this sum is -4. Okay. Now, of course, well, that can't be right for a number of reasons. First of all, these are all positive things that you're adding together. You can't possibly get -4. So what's the problem? The problem is that this formula is only valid when the absolute value of R is less than 1. In this case, our R is 2. The absolute value of 2 is 2, which is greater than or equal to 1. So this series, we can just automatically say diverges. And it diverges since the absolute value of R, which is just the absolute value of 2, is greater than or equal to 1. Okay, so be careful. Don't just sort of blindly, take that formula and start plugging things in. You first need to check your value of R to make sure that it converges. Then once you know it converges, you can use the formula to help you determine what value it converges to. All right, now that we've worked through a few examples of determining whether or not these geometric series converge or diverge, let's pause a moment for a knowledge check. So I want you to take a look at the series below, and I want you to determine whether this series, first, does it converge or diverge? And if it does converge, to what value does it converge? So the video is going to pause, and I want you to take a moment to determine whether this converges or diverges. Okay, great. When I first take a look at this, the first thing I notice is that it's not quite in the usual form. I do have a times r to the n, but my sum is starting at 1 instead of infinity. So in this case, I'm going to do the same thing I did before. I'm going to start by saying, well, what if it did start at 0? Now, in that case, I would have an a of 2 and an r of negative 2/3. But the absolute value of r is the absolute value of minus 2/3, which is just 2/3, which is less than 1. So this does converge. And now that I know it converges, I know that it converges to a over 1 minus r. My a is 2 over 1 minus my r is negative 2/3. I'm going to do 1 minus negative 2/3. So this will be 2 over, this will be 1 plus 2/3 or 5/3. And so this will end up being 6/5. So this series does in fact converge. Oh, sorry, it does in fact converge, but we have to be careful about what it converges to, right? This is the sum starting at 0. I want the sum starting at 1. So what do? Right? I use the fact that now I know the sum n equals 0 to infinity of 2 times minus 2/3 to the n is equal to 6/5. Now I'm going to rewrite this, break off the 0th term. When n is 0, I just get 2 times negative 2/3 to the 0, which is 1. So 2 times 1 is 2. So I get 2 plus the sum n equals 1 to infinity of 2 times minus 2/3 to the n. That's equal to 6/5. And now I simply subtract 2 from both sides. And that's going to leave me with the sum n equals 1 to infinity of 2 times minus 2/3 to the n is equal to 6/5 minus 2. That's the same as 6/5 minus 10/5, which will give me negative 4/5. And so negative 4/5 in this case is my final answer. Now, I'll point out here, if I were to change this problem, say, ever so slightly, so that, let's say instead of starting at n is equal to 1, it started at n is equal to 2. So what if instead of this, I had starting at n is equal to 2? Well, I do all the same work, but then when I get here, right, instead of just breaking off the first term, I'd break off the first 2 terms. So I'd say, okay, the 0th term is just 2. The first term is 2 times minus 2/3 to the first, or negative 4/3. So negative 4/3. And then I'd have the sum starting at 2. Okay. And then you can see that I would just subtract 2 and add 4/3 to both sides. And so, and I'm not going to work out precisely what this is, but I get that this was 6/5 minus 2 plus 4/3. Okay. And again, you could do this if it started at 3, right? You just write out the first 3 terms, so on and so on. Okay, but you can, once you know how to deal with the geometric series that begins at 0, you can deal with the geometric series that begins at any other term. It just might involve adjusting a term or 2. All right. Well, we can sort of summarize this, right? The geometric series, a times r to the n, converges if absolute value of r is less than 1 and diverges otherwise. And notice here, I've sort of dropped 2 things here. I've dropped I'm assuming this is an infinite geometric series, but I've dropped the where it starts, because it actually doesn't matter where it starts to determine whether it converges or diverges. It's just the value of r here. And I've dropped what it converges to, again, because if I don't know where it starts, then I don't know exactly, how far it might I don't know exactly to what value it converges, but I can determine whether or not it converges solely based on that value of R. Okay. But the problem is, as the sort of title here indicates, there are a lot of series. And this theorem tells us how one specific type of series behaves, but there are a lot of other series to deal with. So not all series are geometric. When we talked about sequences, we also talked about arithmetic sequences. You could deal with arithmetic series. They're not particularly interesting in part because they almost always diverge. Again, there's an almost there because the constant sequence 0 is arithmetic. So the series 0 plus 0 plus 0 plus 0 does converge. All the rest of them diverge. Okay. But for example, like here's an example of a perfectly good series, which is neither geometric nor arithmetic. Okay. So, if we wanted to understand this, right, we could start writing out some values. So, this would be 1 over, when n is 1, that'd be 1 squared, plus 1 over 2 squared is 4, plus 1 over 3 squared, that's 9, 1 over 16, 1 over 25, so on and so on and so on. It's really a lot harder to understand like what ought to be happening here, right? And the sort of trick we played with geometric series where we sort of took a partial sum and multiplied by, like, that's not really going to work here. We're not going to get that same sort of cancellation, okay? So we have to come up, I mean, this looks fairly simple, right? As the sort of the terms of the series are fairly simple. But we got to sort of try and figure something out to determine what's going on here. Okay, well, again, you could try sort of going back to the definition. In fact, sort of I think a good rule of thumb in math is when you don't know what to do, go back to the definition. And so, right, I could sort of just come here and start writing out partial sums, right? So, I had this was, 1 plus a half, or sorry, plus a fourth, plus a ninth, plus a 16th, plus, a 25th, so on and so on. So, I mean, I could start trying to write, so the sum of the first one term, oh, that's just 1. The sum of the first 2 terms, that's 1 plus a fourth. That's going to be 5 fourths. Okay. The sum of the first 3 terms, so that's going to be 1 plus a fourth, excuse me, plus a ninth. So let's see, that would need to be in terms of 36ths. So let's see, that would be 36 plus 9 plus 4. So that would be 36 plus 13, which would be like 49, 36. And what you may already starting to see is like it's not immediately obvious like any sort of pattern that's going on here. We could keep going here, but I'm actually not going to bother with your time, in part because in terms of the fractions, I don't see a nice way to represent this, but maybe I could just ask the computer to calculate a bunch of the partial sums. So in fact, that's exactly what I did. So I plugged this into a software package called Mathematica. And these are going to be probably super small and hard to see, but I basically just ask it to print out, let's see, I think the first, 1,000 or so terms. If you zoom in and you sort of track down here, you'll see that as you get towards the bottom, the numbers start to look fairly consistent at about 1.6 something. Okay. But still, this is only sort of evidence of the first, several thousand or first few thousand terms. It appears that this is going to something like 1.64. But again, this is like no proof of anything, right? This is just sort of evidence that, well, when we added up the first however many thousand terms, right, I got about 1.64. Now, it turns out we're going to learn ways to prove that this converges. But what I want to illustrate here is that there are really always 2 separate questions. The first question is always, does the series converge or diverge? And then the second question is, if it converges, what does it converge to? The first question is hard, right? Does a series converge or diverge? As we'll see, we're going to learn lots of tests. It's a hard question. An even harder question often is, well, even if I know it converges, what on earth does it converge to? It turns out here that this does converge to about 1.64, but in fact, I can tell you exactly what it converges to. This converges to pi squared over 6. Okay. Why? It would take us quite a long time to explain why this converges to pi squared over 6. You can see that that value seems to be about right because pi squared, if you think pi is roughly 3, that would be 9. 9 over 6 would be 1/2, or sorry, 1.5. But this is actually a little bit bigger than, pi is a little bit bigger than 3, so this is a little bit bigger than 9, so a little bit bigger than 9 over 6. That seems about right, right? But again, this is really sort of amazing that this happens. In fact, you're taking a bunch of rational numbers and adding them together, and you're getting something irrational, right? Which again, only can sort of happen because we have this infinite sum. So there's some really interesting stuff going on here. We're going to end up mostly in this course dealing with the first of those two questions, sort of how can I determine that this does in fact converge? And then what we'll see is, well, if I know it converges and I want a good approximation of it, then I can just use the computer. Okay, the computer will calculate, if I know it converges, then I know if I take a bunch of terms and add them together, it's probably going to get pretty close to what the series converges to. But first, I need to know whether or not it converges. All right, now some other weird things can happen. So let's think about this series. Use that marker. So if I start writing out terms of this series, so when n is equal to 1, I'll get -1 to the 1, which is -1. When n is 2, I'll get -1 squared, which is 1. And you'll pretty quickly start to see the pattern. Now, this example is your warning to not try and apply your intuition to infinite series. Because I think every reasonable person would look at this and say, well, that's got to be 0, right? Because, well, that'll add to give 0, and that'll add to give 0, and that'll add to give 0, and so on and so on. But the first reason you might doubt yourself is you might say, well, you took and you paired these and these and these, and they all add up to 0. You add up a bunch of zeros, you get 0. But what if I left that one alone and then started pairing these? Okay, well, then I'd get -1 plus 0 plus 0 plus this would pair up plus 0 plus 0 plus 0. And I would say, well, no, then it must add up to -1. And both of those seem sort of reasonable, but they're both wrong. Okay, and so what we have to do here, and actually the problem you're having is that you can't sort of apply this notion of associativity that you have for finite sums to infinite sums. So I need to be a little careful here. And I need to go back to my definition, okay? Think about the sequence of partial sums, okay? What's the first partial sum? The first partial sum is just the first term, -1. What's the second partial sum? That's the sum of the first two terms. That's going to be 0. What's the sum of the first 3 terms? The third partial sum. Well, that's -1. And you start to see that this sequence of partial sums goes -1, 0, -1, 0, -1, 0, so on and so on. And that sequence does not have a limit. There's no value that it gets close to as n goes further and further out, because it's bouncing back and forth between 0 and -1. Okay, so this is an example of a series which diverges, because this sequence of partial sums here does not converge. The sequence of partial sums diverges. Therefore, the infinite series also diverges. Again, this is one that I think can be a bit confusing as you're first getting used to infinite series. It feels very much like maybe this should be 0, but in fact, it's not 0. You could also argue it feels like it should be -1, but it's not -1. In fact, by our definition of convergence of an infinite series, this infinite series diverges. It does not converge. All right, now we're going to look at one more example of an infinite series, and it's one that is actually at first a very difficult series to deal with, although we'll again come up with techniques later for determining whether this converges or diverges. So this is the series sum n equals 1 to infinity of 1 over n. So this is just 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5. Okay, so on and so on. Again, sort of like that 1 over n squared example, there's not going to be a lot of really good ways to, right now, to analytically deal with this. One thing we could do, of course, is like plug it in a computer and see what happens. You could start calculating, right? S1 would just be 1. S2 would be 3/2, right? 1 plus 1/2. You can keep doing this. So I'm going to jump ahead. I calculated the first 10,000, and that got me 9.78. And this might be where you go, oh, okay, 10,000 terms out. Wait, maybe we sort of slowed down, right? And I might go and add in a few more, right? I might go out 11,000 terms. And if I add up the first 11,000 terms, I should write, this is approximate, this is rounded. I'm going to go up a little bit more. Okay, so I've gone up, 1,000 more terms, and I've only gone up by 1/10. Okay, maybe I sort of feel like maybe I'm sort of leveling off at 10, right? Let me go out a little further. Okay, if I go a little bit further, I'm going to go actually a lot further. So I'm going to go from 11,000, I'm going to go to 10 million. I'm going to take the sum of the first 10 million terms. That's going to be approximately 16.695. And now I'm really unsure what's going on here. It's certainly growing very slowly, right? Like 10 million terms, and I'm not even to 20 yet, all right? So it's growing really, really slowly. At the same time, it's hard to tell if it's like leveling off at something or not. Right now, this is sort of hard to deal with. Now, there is a way of doing this, okay? And the way to sort of think about this is to consider, again, go back to the definition, what's the sequence of partial sums? But in this case, we don't want to consider them directly. So what we actually do, and I'm not going to spend a lot of time on this because it's something I want you to see. It's not something you're going to be tested on. If I were to write these out again, so 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7. It's probably enough terms. Okay. So what they actually do is you look first at the first partial sum. Then you look at the second partial sum, or sorry, no, then you look at the third partial sum. Okay. And what I'm going to do is I'm going to notice that's 1 plus 1/2 plus 1/3. Okay. But this is bounded below. Let's see, I can make each of these smaller. So looking at the first partial sum, so I'm not going to look at every partial sum. I'm just going to look at some of them. So I'm going to start by looking at the second partial sum. Okay, so the second partial sum is 1 plus 1/2. And I'm not going to calculate that directly, although I could easily enough, right? But I'm going to notice that that's greater than 1/2 plus 1/2. So all I've done is made that one smaller, and that's equal to 1. Now I'm going to look at the fourth partial sum. Okay, so the sum of the first four terms. Okay, and now what I'm going to do with that, so that would be 1 plus a half plus 1/4, or sorry, plus 1/3 plus 1/4. And now what I can do here is I can do the same sort of estimate on the first two terms and then replace each of these with a fourth. And so here, what I can say is that, sorry, this is greater than 1/2 plus 1/2 plus 1/4 plus 1/4. So here I've swapped out the 1 and the 1/2. So we're going to look at this last example. If I sort of just write out terms here, this would be 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5, so on and so on. And you could start trying to calculate partial sums. In fact, I sort of have some of them pre-calculated out here for you. So, right, obviously the first one would just be 1, right? The second one would be 3/2. But let's skip a bunch and let's say we go to the 10,000th one. That would be roughly 9.78. Now, at this point, you're feeling like, okay, it's 10,000 terms, it's only at 9.78. So maybe it's slowing down, it's sort of converging to some value. Let me go out a little further. Maybe I've got 11,000 terms. That would give me roughly 9.88. Okay. And this is the point where I would probably look at it and go, well, maybe it's leveling off at 10 or so. Let's skip a bunch more terms. Let's go out to the 10 millionth term. That's going to be roughly 16.695. It's certainly not leveling off at 10. And now I'm really sort of confused, right? It's not very big for having gone out 10,000 terms, which makes me feel like it's leveling off. At the same time, it is still increasing a non-trivial amount each time. It's not clear to me whether it's leveling off or it's going to continue to go off towards infinity. Now, there are methods for determining this by looking at and estimating partial sums. Sort of roughly the trick is that you look at the sum of the first two terms and you bound that below by something. Look at the sum of the first four terms, bound that below by something. Sum of the first 8 terms, bound that below by something. And what you eventually show is that your partial sums are bounded below by something that's going off to infinity. And so this series has to diverge. Okay. For the time being, we're just going to take as a fact that this series diverges. And in fact, this is a special series. Maybe it's not surprising, like these are really nice terms, right? So this series actually has a special name and is called the harmonic series. We'll be discussing the harmonic series more, but for now, we'll just leave it as a fact that the harmonic series sum 1 over n diverges. All right, so before we finish this video, just a few words of caution that we've seen along the way. The first is that looking at only part of the sequence of partial sums can be misleading. There's sort of a famous quote that the harmonic series is known to diverge, but has never been observed to do so. So what that's really saying is, like, if you started right now and for the rest of your life computed as many terms of the harmonic series as you possibly could, the value of the harmonic series still wouldn't be very large, right? It grows very, very slowly, even though it does go to infinity. So it goes to infinity, but very, very slowly. So looking only at sort of that first part of the sequence of partial sums can be really misleading. The second word of warning is the intuition about sort of cancellation or other sort of facts of addition that you know are true for finite sums, when you have a finite number of terms you're adding together, they may not carry over to infinite series. So like that example we saw where we were adding together -1 + 1, -1 + 1, -1 + 1. We have to be careful about applying sort of notions of cancellation because those can lead us astray. At the end of the day, right now, what we can do is go back to the definition of convergence of an infinite series. An infinite series converges if the sequence of partial sums converges. And so for now, those are the tools we have and can fall back on when we need to try and determine whether or not an infinite series converges.